Determine if each sequence converges or diverges. If it converges, determine what it converges to. To do this, we'll treat the formulas for the terms in the sequence as a function of n and determine the limit as n approaches infinity. If the limit equals L, then the sequence converges and converges to L. If the limit doesn't exist, the sequence diverges. Notice the first formula for a sub n involves factorials. For a quick review, recall that n factorial is equal to n times n minus 1 times n minus 2, and so on. Before we determine the limit of a sub n, let's see if we can simplify this formula by expanding the larger factorial, which would be the denominator of 2n plus 1 factorial. So we'll leave the numerator as 2n minus 1 factorial, and we'll begin to expand 2n plus 1 factorial. Well, we know the first factor is 2n plus 1. To get the next factor, we subtract 1. 2n plus 1 minus 1 is 2n. The next factor is going to be 2n minus 1, and so on. The remaining factors of 2n plus 1 factorial will be 2n minus 1 factorial. Notice in this form we can simplify because 2n minus 1 factorial divided by itself simplifies to 1. We now have a simpler formula for a sub n. A sub n equals 1 divided by the product of 2n plus 1 and 2n, which if we wanted to, we could multiply and write it as 1 divided by 4n squared plus 2n. And now let's find the limit of a sub n in this form. We have the limit as n approaches infinity of 1 divided by the sum of 4n squared and 2n. In this form, it's pretty clear. As n approaches infinity, the denominator increases without bound, and because the numerator is 1, the fractions get smaller and smaller as n approaches infinity, and this quotient approaches 0, which is the value of the limit. This indicates the sequence converges and converges to 0. And now let's look at the second example. We have a sub n equals the quantity e to the power of n plus e to the power of negative n divided by the quantity e to the power of 3n minus 4. Again, we do want to try to simplify or change the form of this formula before we determine the limit. Remember, when we have polynomials in the numerator and denominator, we can divide each term by the highest power of n from the denominator. We'll use the same approach, and here we'll divide each term by the highest power of e in the denominator, which is e to the power of 3n. So now we'll divide each term in the numerator and denominator by e to the power of 3n. This will give us e to the power of n divided by e to the power of 3n plus e to the power of negative n divided by e to the power of 3n, all divided by e to the power of 3n divided by e to the power of 3n minus 4 divided by e to the power of 3n. And now remember the exponent rule. When we're dividing and the bases are the same, we subtract the exponents. And now let's simplify the quotients. We now have a sub n equals e to the power of n divided by e to the power of 3n equals e to the power of n minus 3n, or negative 2n. And then we have plus e to the power of negative n divided by e to the power of 3n equals e to the power of negative n minus 3n, which is negative 4n. And all this is divided by e to the power of 3n divided by itself simplifies to 1. We have 1 minus 4 divided by e to the power of 3n. Let's do one more thing. Let's go ahead and write the numerator using positive exponents. E to the power of negative 2n equals 1 divided by e to the power of positive 2n, and then plus e to the power of negative 4n equals 1 divided by e to the power of positive 4n. And this is still divided by 1 minus 4 divided by e to the power of 3n. In this form, though, we can more easily determine the limit. So now we'll determine the limit as n approaches infinity of a sub n in this form. As n approaches infinity, e to the power of 2n, e to the power of 4n, and e to the power of 3n all approach infinity, and because the numerators are constants, each of these fractions gets smaller and smaller as n approaches infinity, and approach 0. So this approaches 0, this approaches 0. 1 is not affected by n, and 4 divided by e to the power 3n also approaches 0. Simplifying, we now have the limit is equal to 0 plus 0 divided by 1, or 0 divided by 1, which equals 0. So once again, the limit exists and is equal to 0, which indicates the original sequence given by a sub n converges and converges to 0. And before we go, let's take a look at both of these graphically. To look at these graphically, we'll look at ordered pairs on the coordinate plane in the form of n comma a sub n, and I entered in the original formulas before we simplified them. Here we have the first example where a sub n involves the factorials, and now we'll plot the first 50 points, where keeping in mind the y values of the points are the terms in the sequence. We can see from the graph the terms quickly approach 0 and do converge to 0. And for the second example, involving the exponential terms, again, we'll have points in the form of n comma a sub n. Now we'll graph the first 50 points, and once again, we can see from the points, the values of the terms quickly approach 0 and do converge to 0. I hope you found this helpful.